Okay, we're ready to talk about a very important topic, especially moving into inferential statistics. And this deals with what's called the central limit theorem, which I'll abbreviate CLT from now on. And don't worry about this next part, but it ties into what's called the sampling distribution of X bar. Okay, so what we're doing here is we have some random variable X, okay? So to help you, just think about a student GPA, all right? So that's my random variable X if you need a concrete example. And the idea is I don't know what the average GPA of a UCC student is, and so I'm going to take a sample of some size. Okay, and we remember we denote the sample size with the letter N. All right, and then we're going to compute X bar. And remember, X bar is the sample average. All right, so what we're going to want to do, what we need to know is and look at is the theoretical behavior of X bar if I repeat the process. Okay, and what I mean by repeat the process, I take another sample and compute X bar. So I'll compute X bar again from that new sample. And then I just keep repeating that process over and over and over. So I get all these different X bars. Okay, so I'm going to show you this with a few videos and pictures. It's a little bit deep, and we'll get to some pretty basic results. And then we'll look at some examples of how this behaves, but it's very important for understanding what happens later throughout the rest of the course. All right, so we're going to start with a very simple example to show you the idea of what the central limit theorem is and what it says. Okay, and so we're just going to take a fair die. All right, so just a single die. We're going to roll it and observe the number. Okay, and so then our random variable then is X is the number rolled. All right, its possible values are 1 through 6, and this is called a uniform distribution. And so it takes each one of those values, since it's a fair die, with equal probability. So that is the probability distribution function. All right, and what I'm going to do here is I'm going to roll it 100 times. Okay, like that. This is just kind of interesting in and of itself because we expect to get an equal number of 1s as we do an equal number of 3s as we do an equal number of 6s, since that die is fair. So I'm going to show you a simulation of me doing that. Alright, so I used a random number generator in Excel to do this, and so this first number right here means that I rolled a 6 on the first try. Look at this, this is kind of interesting. I rolled 3 6s in a row, and then I start to roll through. You can see that I'm getting all these different rolls. I'm just scrolling down if you're wondering why the numbers are changing. And so these are just all the different rolls that I get. And then notice right here I rolled 100. That 100 kind of disappeared. Interesting there, I rolled 3 6s at the beginning. I also rolled 3 2s at the beginning. So I do have a data set. I have a data set of 100 rolls, and so now I can make a histogram. And well, first I can compute the frequencies of each roll, and then I can make a histogram of those rolls, a frequency histogram. Remember, since all those probabilities look the same, we would expect those bars all to be about the same height in the histogram. So here's a summary of the results. Sorry about all this glare over here. That's just from my iPad. But anyway, right here I made a frequency table. So here's my value of X. Here's the frequency. This is slightly interesting here. Notice you don't get equal numbers of frequencies. And so if anything else, this is just a good illustration of randomness in practice. Although we expect equal numbers, we can't actually expect them because of randomness. And so you can see I rolled 6 more 1s than I did 2s, 20 minus 14 there, etc., etc., and I rolled more 6s than anything else. Now, there is some issues we won't get into about number generators simulating really random things. But let's just assume that that's true. So I go and make my histogram. Remember, if those probabilities were perfect, we would have expected all those bars to have right about the same height. But you can see that we have this we have this peak over here, and then this big trough down at three and so on. So not what we expected. So like I say, it's a good illustration of just randomness at work. Okay, now one thing I can also do too, and you can see it down at the bottom though, is that I can compute the average of all those rolls and the standard deviation. And so that's a sample average. I took 100 rolls, so the sample average is really 3.6 if I rounded correctly. And then the standard deviation is about 1.8. Okay, so keep those numbers in mind in a minute. So now what we're going to imagine doing is doing this a bunch of times, and you got to remember what the it is when I say doing this. It's repeating the entire process. Okay, so I rolled the dice 100 times, got these results. I'm going to do it again, so I'm going to roll the dice another 100 times, get a different set of results. Roll the dice again 100 times, get a new set of results. So I'm taking these samples of size 100, but I'm going to take a bunch of them. I'm actually going to take 100 of those samples. And so there's two kind of repeating things going on. I'm repeating the die roll, okay? And so whenever I repeat the die roll and collect those, that is one sample, okay? But then I'm going to repeat that whole process, and so I'm going to get 100 samples as well, all right? And what we want to look at is, and after we compute each sample, we're going to do what we did down here. I'm not going to make a histogram for each one of them, but what I'm going to do is for each one of those samples, I'm going to compute X bar. Okay, so let's look at what we're looking at here. If you looked carefully at those numbers, this is my first sample right here. So that's that first set of numbers. There's actually 100. They keep going down even further. I started to make a video, but that scrolling gets a little bit wonky. And so then I rolled the die 100 more times. So here's my second sample right here. Okay, and then again, there's more down there. All right, and then after I rolled the die and the second 100 times, then I did it again, and so there's my third sample, like that. And so what's going to happen here in a minute, after I get each sample, I'm going to compute X bar from that. In that last example, what was it, 3.1? I don't remember exactly. And then for this second sample, I'm going to compute the sample average of it. Okay, and then for this third sample, I would compute the average of it on down the line. I didn't scroll all the way over where you could see them, but I have 100 samples as well. Okay, the question is, what do you think? Are these two going to equal each other? Are these two going to equal each other? Etc., etc. And that ends up being a big question to understand the answer to. All right, so if you look carefully at this, all these numbers are part of the bottom halves of my samples, all right? And then down here, you see that blank line, and then like that 3.8 that this one's pointing out, that's an X bar value. So I had it compute the average of each one of those samples, all right? So I don't know if you can see it, but, oh, here. There we go. Just my screen was a little bit weird. All right. So here's that first sample average that we got, that 3.6. All right. And then look, in the second one, I got a different number for X bar. The third one looks the same. Let me make it bigger now that I have it. The third one looks the same. It's actually slightly different because it's just coming out to 3.4 because of rounding. But then notice I get 3.6 again right here, and then I get 3.5. The key thing to notice, and see, I actually have 100 of these. You can't see them all in the picture, but there's several of them here. And so notice that the average isn't coming out the same each time. Okay, that in and of itself is a big concept right there. X bar varies from sample to sample. So what does that mean? All right, that means that X bar itself is random. It depends on what happens with the sample you take. And so what we're getting at here, very big concept, X bar is itself a random variable. Okay, well, how do we describe random variables? we describe them with their probability distribution. And so what we're getting at here is that x bar has a probability distribution. Okay? And the question is, what kind of probability distribution does it have? And that's what ends up getting captured with the central limit theorem. The central limit theorem actually describes the probability distribution of x bar, and it's an amazing thing. So now what I'm going to do next is I'm going to record all those x bars. So you remember the first one was 3.6, the second one was 3.4, I got 3.4 again, I'll write down a few more of them. I got 3.6, 3.5, 3.3, 3.8, etc., etc. So I have 100 of these averages. Okay, so this is a data set right here. It's a sample of samples in a sense, okay? But this is a data set, so I can make a histogram from this, all right? And so I can determine my number of classes, figure out the class width, etc., etc. Remember that long process. But then I can make a histogram of this, look at it, and hopefully get an idea of its shape and maybe make some kind of conclusion from there. So yeah, let's see what happened. I went ahead and made everything so we can just look at it. So this is just a rough histogram. I didn't format anything like the x-axis. Looks like we have different numbers. But what I did is I took each one of these averages I took all 100 of these averages and I created categories. I made 10 categories, and they started at 3.05. They went up to 4 and so on. So, just I'm bugged by that bottom thing. I probably should have done that. But this is 3.05, and this is up to 3.14, etc. And then it goes up to 3.2 and on down the line. Okay? And so that's what we have here. What we want to look at is the shape. Now, because of some randomness, we have this weird bin down here, category down at the bottom that had quite a bit of frequency. But if you look at the overall shape, what do we see? But what do we basically see here is we see the idea that this thing is roughly bell-shaped. It's amazing. Okay, and again, if you've seen those problems where they say things are approximately normal, this is kind of where it's coming from here. It's not perfect, but at least in some sense, we are seeing that bell shape, at least approximately, especially in the middle here, where we see that mounding in the middle. Okay, and so that's the idea, is that, and what the central limit theorem will end up saying, is that we could have a variable that's not normal whatsoever. But then if we go and take samples of it and compute the average of each sample over and over and treat that set of averages as a new sample, that sample will be approximately normal. It's an amazing fact, and it's a fact of nature. And one other quick thing to show you before we state the central limit theorem. If we go back and look at that very first sample that I took, its average was 3.6 and its standard deviation was 1.8. Now again, we're thinking about looking at that big sample of sample averages. Okay, so all those x bars like that. If I took the average of all those x bars, I got 3.5. So notice these two are pretty close to equal. Okay, they're not perfectly equal, but they're not close to equal. But if you look at those standard deviations, for the single sample, S was equal to 1.8, but for the sample of averages, so for the sample of x bars, its S is 0.2. Notice that that number right there is much lower. And what that's saying in the deeper picture is, although we could have a variable with quite a bit of variation to it, whenever we start forming samples and computing their average, the average of all the samples, that average has a lot lower standard deviation. That's another fact of nature. Now we're ready to get to the central limit theorem. All right, so we're ready to say what the central limit theorem is telling us. All right, and so the idea is that I have some random variable x. It has a mean and a standard deviation. And to stress the variable, we're just subscripting it with that x. Okay, and so what the idea is, we're taking samples of in and computing each sample's average. So we have a bunch of different averages, one from each sample. Okay, and then what we saw is that x bar is a random variable, and so it has a probability distribution. And the central limit theorem says what that probability distribution is, at least approximately. Now, it starts with this phrase that we'll talk about in a little bit, but it says for n sufficiently large. So we need our sample size to be sufficiently large, and we'll talk about what that means in a minute. But then what the central limit theorem says, it says that x bar is approximately normal, okay, with, and we can say what the mean and standard deviation is of x bar. Okay, now if you think back to that that last slide that I was just showing you, it looked like the mean of the averages was about the mean of the original variable, and that ends up being true. So it looks pretty uninteresting right now, but remember we saw a much smaller standard deviation with the averages, and what the central limit theorem says is that you take the original standard deviation and you divide it by the square root of n. Okay, so this is a huge theorem in statistics and probability, and it really is just kind of a statement about nature too. It's very strange that you can start with some kind of random variable. It could have its own mean and standard deviation. That standard, the standard deviation tells you about variance, so you could have very little variance or a lot of variance in it. But if you go and start taking samples of it and then computing the average of each sample and look at the behavior of those averages, they all behave just about the same. That they'll be approximately a bell curve, so they're approximately normal, and then the mean will be the same as the original variable, but the standard deviation is much smaller. Whenever we divide by the square root of n, we get a much smaller number. What that says is that mean-wise, averages behave almost just like the variable do, but they have much less dispersion or variation in them. Okay. One other quick thing to say, just in terms of the notation, is we could summarize this by saying x bar, use that tilde, approximately normal. Its mean would be the mean of the original variable, but its standard deviation would be the original standard deviation divided by the square root of n. All right, so let's talk about what this murky phrase at the beginning, insufficiently large, means. All right, so yeah, that's the only thing that's kind of murky with the central limit theorem, is this phrase right here, for n sufficiently large, or if n is sufficiently large. What the heck does that even mean? And so we'll break this into two basic branches here. Is that, remember, we started with some variable. In the last case, it was the die roll. All right, or it could be like student GPA or something like that. Okay, so if we know from the get-go that our original variable is normal, all right, and so if we know that we're dealing with a normal variable from the get-go, there's no approximate about it. X is normal. Okay, x bar is normal. There's no approximate in the CLT, and n can be any size. All right, and so there's no restriction on the sample size if we're starting with a normal random variable. Okay, if we don't know that we're starting with a normal random variable, then this is going to seem a little bit strange, but you got to remember, I've mentioned this a few times, statistics really started in the early 1900s, and the way the theory began was with people looking at many data sets and analyzing their behavior. So some of the rules that we use in statistics aren't exactly deductive. They're not deduced from probability laws, but they're observed empirically from observation. And so a general rule that people use whenever we don't know that our original variable is normal is that we need the sample size to be at least 30. Okay, and you can see it's not perfect. We were using sample sizes of 100 before, and we still didn't have a perfectly normal looking distribution. And so it's not perfect, it is approximate, but that is the general rule. So if you want to use the central limit theorem to deduce things, Either you need to be starting with a normal variable, then you don't need to worry about what sample size you're dealing with, or you need your sample size to be at least 30. You need to be taking at least 30 measurements in each one of your samples. Okay, now we're ready to look at this in terms of problems. All right, so first let's look at this. Let's just use the fair die roll. All right, remember this is its probability distribution. Knowing that you have a test coming up, why don't you practice this? How do you find the mean of x and the standard deviation of x? So this is where you go and plug things in on your calculator or Excel, and you got to get it to find the population mean and the standard deviation. So just to remember what you do, you type this in on your if you're using your calculator, you type those two columns in on your calculator. So here's what I use the calculator, and so that's what I typed in for my L1 and L2. Make sure you realize what I typed in is 1 divided by 6, and then my calculator converted it to a decimal. So now remember what I do. I go back to my stat menu, and I want it using both lists, so I tell it to use both of them. By the way, this is funny. That's blinking, but every time I tried to take the picture, it was black. So anyway, but that's the calculate part, and so then you would hit enter right there. And also remember too, if you have one of the older calculators, we're always doing one variable stats, and then you just need to tell it to use list 1 and list 2, and then you would hit enter. So then here's what I'm looking at for my one variable stats, and so remember we're looking for mean and standard deviation. So here's my mean, here's my standard deviation. Now in terms of rounding, you got to remember what your variable is. It takes values 1, 2, up to 6, right? Those all go down to the ones place, and so I want to round these to the tenths. And now remember, your calculator's dumb. It doesn't know we're dealing with probability and a population, so this is really mu is 3.5. And then for the standard deviation, we round it to the tenths, and so we get 1.7. All right, so now we're ready to roll. So the mean of our original variable is 3.5. The standard deviation is equal to 1.7. Now, one quick thing before we move on too. Remember, we're about to get to talking about the central limit theorem and using it, but remember what the sample size depends on whether or not our variable is normal or not. Is x normal here? Pause it and ask yourself that. Okay, is x normal? But the answer is a very clear no. Remember, a normal variable needs to have that bell shape. These probabilities right here, if I drew a histogram of those, they would all have height 1/6, and so that's not bell-shaped at all. So our original variable is not normal at all. Now you may want to look at these two questions and ask yourself why they're different. All right, and so if you need to, pause it real quick, but then I'm going to move on. But the first question's asking for the probability that x is between 2 and 3. Okay, and so what's very different about that, we're just talking about x right here. That's a single die roll. Okay, and so if we're just talking about x, we would use the original probability distribution that we were given. And so this is just like problems that we're used to seeing. This is actually a discrete variable, and so this is just going to be the probability that x is equal to 2 plus the probability that x is equal to 3, which is 1/6 plus 1/6, 2/6, or and so that's about 33.3%. All right, so on about 33.3% of single rolls, then we'll roll either a 2 or a 3. Now what's different in this second problem, we're talking about a sample of 50 rolls. All right, and so we're talking about rolling a die 50 times, then doing it again, computing the average of all those rolls, then doing it again, rolling a die 50 times and computing the average of all those over and over and over again. And we're asking, look at the variable in the middle here. We're asking about the average. We're asking the probability that the average is between 2 and 3. Okay, now how does this tie in? N is equal to 50 here. That's bigger than 30. Okay, and so since we have a sample size that's bigger than 30, the central limit theorem applies. Okay, and so what that says is that x bar is approximately normal with mean, the original variable, and standard deviation, the original standard deviation, divided by the square root of n. Now our n here is 50. In general, it's the square root of n. So make sure you realize from problem to problem that could change. And so there's our normal random variable. Now we just fill things in, and so that's normal. The mean was 3.5. The standard deviation was 1.7 divided by the square root of 50. Now be careful of round off error too. Just whenever you type in the standard deviation, I would just type in that number. It's not that big of a deal just to type it in. You could go and compute it and write out a long decimal form of it. But just keep it the way it is, and just type that number in the form. Now the key thing now is this is a normal problem. This is no longer a problem about a discrete variable. This is about a normal problem. And so we'll be using the ideas of normal distributions. Here we have this mean of 3.5, and now we have a normal distribution above it. Now what are we doing? We're doing the probability that x bar is between 2 and 3, right? Like that. And so 2 and 3 are to the left of the mean here. So here's 2. Here's 2 and here's 3, and what are we trying to do? We're trying to do the area between those two numbers right there. So you got to remember what two numbers we're doing. Sorry, I'm drawing so small. But so yeah, we're doing a normal probability of being between 2 and 3. So you probably want to pause it a second to make sure you remember how to do this. But the idea is we're doing the probability that the x bar is between 2 and 3, but now we're taking advantage that this is a normal variable. So we're going to use it, and we're computing the probability of a normal variable. So we're going to use that normal CDF function, or the norm.dist function, okay, whichever kind of software you're using. Now remember, to do these kind of probabilities on the calculator, you just type in what two numbers you're between. So we're between 2 and 3, and then we'll use our mean of x bar, and then we'll just type in 1.7 divided by the square root of 50 for our standard deviation. All right, remember it's a little bit trickier on Excel because we got to subtract two numbers. In Excel, it only does probabilities completely to the left. So you'll do the norm dist from 3, and then do the 3.5 and the standard deviation, like that. Well, I got to point out one thing about that in Excel. And then you'll need to subtract off the area to the left of 2. Hopefully you've just been getting used to that where it makes sense. Okay, so you'll do that. Now, one thing about Excel. There's one thing you could do is you could go into one cell and type in your standard deviation. But, well, I realize however you do it, it doesn't have a square root key on it. So to do a square root in Excel, if you don't know this, you type SQRT and you type in the number. Okay, you could just type that into a cell, and then whenever you go to type in the standard deviation, highlight the cell and it'll fill in the cell name there. Or you could just type those in each time. That's up to you. In any case, what do you get? All right, so hopefully you tried that. I'm going to write it in a second, so you might still want to pause and see if you can get it. But just to summarize, for a single die roll, okay, so if we're just talking about x, we're just talking about a single die roll, then the probability that it's between 2 and 3 is about 33.3%. But if we go and look at a sample of 50 rolls and look at the probability that the average of those rolls is between 2 and 3, if you look carefully, we only get about 1.9%. So it's much lower, all right? And so the point is, why is that so low? All right, and it all has to do about that standard deviation, that the standard deviation of x bar is our original standard deviation divided by the square root of n. So that was that 1.7 divided by the square root of 50. If you go and actually calculate that number, it's about 0.24, and there's a bunch of decimal places after it. Okay, and so what that says is that yes, now this is for x bar, okay, that we have that normal distribution that's centered around 3.5, like that. But this standard deviation is very small. Remember, the standard deviation of the die roll was 1.7, so this standard deviation is a lot smaller. And so for our single die roll, it's actually the one standard deviation range is pretty big, but for the average, it's pretty small. It's 0.24, and so what we do have a normal variable, but it's very thin, like that. And so then to be able to get values between 2 and 3, there's actually a pretty small chance of that happening. And so that's what's going on. Okay, now let's look at one more example, see if we have it down. So I'm going to go ahead and put these two up, and why don't you pause and see if you can do them. So please do just pause for a minute and try these two and see if you can follow what we've been talking about. Okay, problem 3 should be just like the previous problem, except that we have 100 die rolls, and so to ask yourself how that changes. And then problem 4 has 100 die rolls, but a different probability. So make sure you can get both of these. So please pause, but I'm going to pick up here. All right, so in problem 3, the key thing, the difference here is that n is 100. That is greater than 30, so we can still use the central limit theorem here. And we're doing the probability that we're between two numbers. And so if you're on the TI-84, the key thing is here is that the standard deviation of our average now is the original standard deviation divided by the square root of n, which is now 100. Okay, 100 has a nice square root, so you could go ahead and do that, or just do it like you did the last problem. But the standard deviation here is 0.17. So whichever feature you use, I'm hoping that you tried this, because I'm just going to do the answer here. And so if you go and compute that probability using whichever software you use to calculate it, I hope you realize that's only 0.2%. So with 100 die rolls, it's very unlikely that a sample average is going to come out less than 3. And back in our simulation, you might want to go back in the video and look at that. The minimum average we ever got, I think, was 3.1. We never saw an average that came out smaller than 3. So you can see there's a good illustration of that probability and why it's so small. Problem 3 was just like problem 2, so I did that one quickly. I'll go through problem 4 a little bit more carefully. But the key thing is, now we have 100 die rolls, and so we have that new standard deviation that we could use in problem 3 right there. All right, and so now we're doing the probability that x bar is greater than 3.6. And so in terms of the picture, here's our normal curve. We're talking about being at 3.6. We're talking about x bar being greater than 3.6. And so we're doing the area to its right. Okay, so how do you do that? It depends on your software, whatever kind of program you're doing. So if you're doing it on a calculator that you type in the lower number and the higher number, you would do the normal CDF. And then the idea is that you're going from 3.5 out to infinity, but you just need to plug in a really big number. You could actually even get away with 100 on this one, but you have to convince yourself that that's true. But just plug in a really big number. If you don't like to think, just type in something like 1,000,000, okay? Or you can think about being 5 standard deviations from the mean and type in a smaller number. Key thing here is that I wrote the wrong number there at the beginning. We're going from 3.6 to infinity. Sorry about that. But then our mean is 3.5, and then we type in our new standard deviation. And like I say, you could type in 1.7 divided by the square root of 100, or realize that that one simplifies out so that you could just type 0.17. Okay, if you're using the spreadsheet, I'm going to do it Excel style. So there you do your norm.dist. Oops, sorry. The key thing is norm.dist does the area to the left. So if you just use norm.dist, you would have that blue area right there. But remember, the total area under the curve is 1, and so we would do 1 minus norm.dist, and then we would type in 3.5 or 3.6, sorry, keep doing that, and then the mean, which is 3.5, and then the standard deviation. I'm just going to write 0.17, but just like with the other ones, you could type in that right there. All right, and so whichever way you do it, what do we get as our answer here? So hopefully you tried that out and you see that the probability that x bar is greater than 3.6 is about 27.8%. And now what that's saying, try to think about what the numbers are saying too to get a better understanding of what's going on. We're looking at this probability right here, and then we got this percentage. So what that's saying is that if I go and take samples, if I roll a die 100 times, like that, and compute the average, and then think about doing that over and over and again, the whole process, 100 rolls computing the average, 100 rolls and computing the average, then in about 27.8% of all of those averages will be bigger than 3.6. Okay, here's there's one problem with several questions. Okay, and especially if you feel like you're understanding things, please pause and see if you could figure all 3 of these out. This is an example we've seen. X is going to be the U.S. male height. Those, if you remember, are normally distributed with a mean of 69.5 inches and a standard deviation of 2.1. So in terms of notation, if it's confusing, here's our mu of x, here's our sigma of x. Okay, so in problem 1, what's the probability that a U.S. male height is less than 68 inches? The key word there is, in terms of what we're talking about, is a U.S. male height. And so we're just talking about one single measurement. And so see, this problem I didn't give you it in math notation. We got to interpret it in math notation. And so here we're just talking about the random variable x. So that's the thing. X is just a single U.S. male height. And that's what that word A is telling us. So we're doing the probability that x is less than 78. Okay, or 68, sorry. All right, and so then what are we dealing with? We're dealing with a normal variable, and we're computing a probability. So we're going to be using the, we want a probability, I should say. And so we're going to be using the CDF function, or the norm.dist function. All right, and so go ahead and see if you can finish it from there. This is a problem that we've done. I'm just going to pause and then I'm going to write the answer myself. Okay, and so hopefully you got that one. It is about 23.8%. So of U.S. males, about 23.8% of them have a height less than 68 inches. Now let's look at problem 2. In a sample of 10 male heights, what's the probability that the average height is less than 68 inches? So the key thing to notice here is we're asking about average height. And so we're talking about an average. And so if I wanted to convert that into math notation, we're doing the probability that x bar is less than 68. And here n is equal to 10. Now that's smaller than 30. So why am I still saying that we can use the central limit theorem? And it's because we started with a normal variable. So if we start with a normal variable, to use the central limit theorem, n can be any size. All right, and so x bar is normal here. Its mean is the same as our original variable, so it's still 69.5. But then its standard deviation is going to be the original standard deviation divided by the square root of n. Okay, so this problem is very similar if you're using the normal TI calculators. This is just going to be our normal CDF. All right, we're doing less than 68. So basically we need negative infinity here. Hopefully you got problem 1 to realize what we're doing. So I use negative 1,000 for it. All right, and then we're going up to 68. The key thing is our mean is the same, but we need to type in 2.1 divided by the square root of 10 for the standard deviation. Okay, if you're doing it in Excel, this is one that works just like, or works perfectly for Excel because it only does areas to the left. I realize there's one thing I forgot to write on my previous slides. So here on this one you would write 68, but then you would want to type in this mean and this standard deviation. Remember too, you always have to type true to get it to compute a probability. That's what I forgot to tell you on the last one. Okay, and so what do we get for this one? And hopefully you got that. And so however you did it, hopefully you see that that's about 1.2%. Okay, so let me circle these because things are starting to get a little cluttered on here, aren't they? So yeah, so make sure, why is this probability so much smaller? Because we're looking at an average. Averages have a much smaller, or a significantly smaller standard deviation. So although it's fairly likely for a U.S. male to have a height less than 68 inches, if you take a sample of size 10, if you take 10 U.S. male heights and average them together, it's pretty unlikely that the average is going to be smaller than 68 inches. All right, and then hopefully you see how to do that. And so the difference with 3 now is that n is equal to 100, and so then our standard deviation that we want to use is going to be that 2.1 divided by the square root of 200, and we're doing the probability that x bar is less than 68 for a sample size of 200 now. So why don't you see if you can finish that? I need to pause it and calculate it. This is interesting. My calculator just gave me flat out 0. What that's telling you, remember our calculator usually uses that scientific notation for really small numbers. So this probability is so small that even to the, I think it's 99 digits that the calculator can get a number to using scientific notation, that number still rounds to 0. So if you take a sample of 200 male heights, average them all together, if that average came out to be 68, yeah, something very, 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 very unlikely occurred. Okay, so I hope that is enough and it helps. And but please, as always, let me know if you need help, especially once you get to the homework.